Hi, in this series of videos, I will be talking about the derivation of the Schrödinger equation from first principles. I will try to show that this kind of derivation, which is an axiomatic derivation, has as its consequences a better understanding of the theory itself. In this first part, I will be talking about introductory issues. What I mean by a physical theory, what I mean by the role of semantics and syntactics in the theory, and how an approach based on axioms, interpreted axioms, can be helpful to understand the theory itself. So let us begin. Let's begin talking about syntax and semantics of a physical theory. I believe that we can portray a physical theory as having two different parts. I know that this is a simplification, but I hope this is not an oversimplification. So let's assume that a physical theory has two different parts. First, it obviously is a theory with symbolic content. Symbolic, of course, mainly mathematical content. But given these, we can divide the theory in two different parts. The first one will be its syntax, which furnishes the symbolic content. We may say that the syntax is the part of the theory that contains the equations and symbols of the theory. For example, an electric field or Maxwell's equations in the case of electromagnetism. But it also must have another element without which it's not a physical theory after all. It must have the semantics, which is how we interpret this symbolic content. So a physical theory has just these two elements that must play with themselves. They are meant as being separated, but of course they must play with themselves in a harmonic way. So let's see how can we manage that. Quantum mechanics. Of course, we know that quantum mechanics has a very solid syntax. We are, of course, mainly interested here with the case of the Schrödinger equation approach to quantum mechanics, non-relativistic quantum mechanics. But we may talk about matrix mechanics and any other approach we want to talk about. And in any case, the syntax of the theory is quite solid. But what about its semantics? Well, we have to interpret the syntax some possibilities. We may have Copenhagen interpretations. There are a variety of interpretations related to Copenhagen. We may have many words interpretation. We may have stochastic interpretation. We may have Wallace or Bohmian interpretation. We may have statistical interpretation, and we may have consistent histories interpretation. And these are but a small content of all the interpretation we may have regarding quantum mechanics. We may cite, for instance, many minds interpretation, which is part or related at least to many words interpretation, and a lot of other interpretations that galore. in the realm of quantum mechanics. So we may say that despite the fact that the syntax of quantum mechanics is quite solid, its semantics is floating away. Our job in this series of videos is to at least try to make this level, the semantic level, also as solid as it can be. We must mention, of course, that not all these interpretations are compatible with one another. In fact, many of them are opposite to many others. So we have a problem of consistency if we try to assume more than one of these interpretations. Okay, but what has axiom anything to do about it? Let's come to the Schrödinger equation itself. We have this equation, very well known, used and abused, and we have at least one first problem with it. The meaning of psi. What is the meaning of psi? We know that historically we find a number of interpretations, very different interpretations about the meaning of psi. Many of them were overcome, but we still have some interpretations which are not equivalent about the symbol of the theory, which is the psi. Does this psi refer to ensembles or single systems? Is this psi related to measurements? And if so, what comes to these measurements? Observers? Are they related to minds? Or are they the reflect of the projection over many worlds? We don't know. This term, which comes to be the energy in cases of a time-independent potential, and the Schrödinger equation goes to an eigenvalue equation, is also not free from controversy. For instance, when we have this as an energy times psi, what does this energy means? It's a mean energy, an average energy, or it is related to measurement, or maybe to dispassionless measurements. And what these dispassionless measurements has to do with the way we construct operations, we form these operations. We know that we have here a problem of operator uh, sequence. We must order in some way the operators because they are not commutative. Okay, so we have this is just a small example of problems that we have within the Schrödinger equation. I know that many of you will regard these problems as solved, but I can assure you that they are not. In the following videos, I will say why they are not and how they can be overcome. At least I hope I will. Okay, and what is the role of the axiomatization? What does it mean to mathematically derive the Schrödinger equation? Does it bring about any advance in our understanding of the theory? Okay, again, our theory has two parts, syntax and semantics. But we now will put between these two levels the axioms, and we will show that if we have the symbols of these axioms already interpreted, then we can gain a lot by treating quantum mechanics in axiomatic terms. And how is this so? Because now we have, from the syntax, a very good control over the emergence of the symbols of the theory. What I'm saying? That if you have an axiomatic theory, every symbol that appears in the theory at some moment must be referred to the symbols already existing in the axioms. They can not be appear from nowhere. They are, in a sense, some combination of the symbols that are present in the axioms. So we you know that they must refer. This is the meaning of this arrow. Refer to the symbols of the theory of the axioms. Refer in the mathematical sense, in the symbolic sense. But we know that we have also a control over the interpretation of the symbols of the theory, because the symbols in the axioms are already interpreted. So this interpretation also must be referred in any point of the theory to the interpretations of the axioms. This is what we call the heritage, the semantic heritage. How the symbols that are appearing in any stage of the theory are referred also semantically to the symbols, interpreted symbols existing in the axioms. And when we do a derivation, a mathematical derivation of the theory, this puts a very strong constraint in our approach. This is so because in this case, every every situation has to be um, reducible to the axioms themselves. Not only that, let me give you an example. We are usually accustomed to present the Schrödinger equation using a heuristic approach in Cartesian coordinates. Then we usually change to a curvilinear coordinate by making this change in the operators. In the case of such a derivation, or like the one we will present in the series of videos, we are not free to do that. We must write the axioms in the desired coordinate system, and from repeating the same steps of the derivation, we must find the Schrödinger equation already written in this new coordinate system. If we can't do that, the method is a failure. So this is a strong constraint. Another strong constraint: any extension of the theory must be a consequence of the extension of the axioms themselves. We cannot extend the theory by taking it in a different point from the axioms. Since the theory comes from the axioms, its extension must come from the axioms too. So this is a very strong constraint. And in what follows, I will show that the mathematical derivations, because we will see a lot of derivations, 5 derivations of the Schrödinger equation, will present exactly this kind of behavior. So this is what I will have to say in this video, In the next video, I will show the first derivation of the Schrödinger equation, which I call the characteristic function derivation. Thanks for watching.